right. Let's take a look at our spell work here. So these problems, both fairly similar to what we were working with yesterday for number 3, although we'll see this second one has a little bit of kind of a twist at the end, but we'll deal with that when we get here. Looking at A, this is cosine of 2x equal to the square root of 3 over 2. So what did I say yesterday that we kind of run into? What's the difficulty that we run into straight away, and how do we best address it / push it off to the side to not have to address it until later? Okay, so the 2x is the main problem here. Otherwise, this would just be like a unit circle question, right? It would be exactly like this. So 2x is the issue, and then what do I say to do in order to avoid having to deal with the 2x? Yeah, we're going to use a dummy variable. The one that I used was u. To say that u is equal to 2x so that we can reformat this as cosine of u being equal to the square root of 3 over 2. Now, in addition to the problem itself, we are also given the constraint that x is going to live between 0 and 2 pi. When it's called parameterize, when I parameterize my equation to be in terms of u rather than in terms of x, what else do I need to adjust here? Yeah, we need to adjust the upper and lower bounds on u. We know them for x, but as it stands right now, we won't know when to stop with u. So we'll adjust those for u as well. If x lives between 0 and 2 pi, then where does u live? Between what two values? 0 and 4 pi. Very good. U is just 2x, so it should be double the minimum, double the maximum. All right. We'll deal with that 4 pi here in a second. We're going to need to reformat it to make it look a little bit prettier. But for now, let's deal with the unit circle question. Cosine of u equals root 3 over 2. What do I get for my possible values of u here? So pi over 6 and 11 pi over 6. And then what do I have to do to each of these to account for coterminal angles? Plus 2 pi k to both of them. Okay, so we know that we're going to be in terms of pi over 6. Denominator is going to be in terms of pi over 6. So let's adjust this kind of upper limit. This is just like setting up our metal detector. So we know as soon as we go beyond this kind of boundary here, what is maybe a better way to write that the maximum is 4 pi? 24 pi over 6 is maybe just like a more convenient way so that we know as soon as we've gone beyond for those values of u that we are good to stop. Now, yesterday, our methodology was just, okay, let's start with k equals 0. What must be true about k as well? One moment before we forget about this. What must be true about k? It's an integer. So this is taking into account all the different possible ways that I could add or subtract 2 pi to find coterminal angles. That's that plus 2 pi k. And our strategy yesterday was, well, we'll just check different values of k and see which of them gives solutions, and then there will be a cutoff where they stop giving us solutions for this particular kind of bound, and then we'll be done. I alluded to yesterday the fact that we could actually figure out some kind of boundary on k as well. It's not too terribly difficult. In particular, if u is between 0 and 4 pi, then we might be able to say something along the lines of like 0 is less than or equal to u is less than, I'm going to write this actually as 24 pi over 6. Something like this. And we have two different u's here. This either means for our first, what we described as a node, that 0 is less than or equal to this first node is less than 24 pi over 6. Let me actually, this is less than 24 pi over 6. And we also get that 0 less than or equal to 11 pi over 6, that second node plus 2 pi k is less than 24 pi over 6. And actually figuring out what k can be is just solving these two equations for k. The first equation will give us what k is allowed to be for the first node, and the second equation will give us what k is allowed to be for the second node. It's not too horrible to do this. So like subtracting pi over 6 from both sides of my first equation here, and then dividing by 2 pi, I'm going to get, well, negative pi over 6 divided by 2 pi is going to be negative 1/12. And then 24 pi over 6 minus pi over 6, that's 23 pi over 6 divided by 2 pi is going to give us 23 over 12. Likewise, subtracting 11 pi over 6 and then dividing by 2 pi, I'm going to get negative 11/12. And you should also get 13/12 on the other side. This is new. This was the technique that we didn't look at yesterday. So if this looks nothing like what you did, it's not supposed to. I'm just showing you the kind of other way to do it. We said that k is an integer. So we are looking for the integer values of k that satisfy these kind of constraints. And so what are the only two integers that live between first negative 1/12 and 23/12? I get 0 and 1. That 0 looks a little bit messy. 0 and 1. And then same thing for negative 11/12 and 13/12. I get that this is also 0 and 1. So the values of k that will work for my first and second node are k equals 0 and k equals 1. Yeah, similar. So that's just solving each of these expressions for k. So whenever you have like this embedded inequality, you solve for k and you do it to both sides of the of this kind of like inequality here. So subtracting everything here by pi over 6 and then dividing everything here by, for my top line, dividing everything here by 2 pi, and I get the bounds, the lower bound of negative 1/12 and 23 over 12. Yeah, you do. Well, you do every operation you do to all three parts. So we subtract pi over 6 from all three kind of segments, and then we divide 2 pi from all three segments. And since we didn't divide by negative, we don't have to like flip any of the inequalities or anything, and we end up with just k on its own. And then same thing for the other one, but of course subtracting 11 pi over 6 rather than pi over 6 and then dividing by 2 pi. Subtract, so you're solving for k. What would you do to like isolate k here? Yeah. Subtract pi over 6 from everything, divide by 2 pi for everything, and that should give you these constraints. So this works. this is fine. These are the values of k, and then we could plug in those values of k and see what the values of u are. That's fine. What was our strategy that we did yesterday, though? That worked perfectly fine as well. Yeah, just check values of k until they stop working for us, right? So like when k is equal to 0, what are our values of u going to be? Yeah, it's just pi over 6 and 11 pi over 6, which notably is less than 24 pi over 6. Both of these are less than 24 pi over 6, so we are still within our bound. When k is equal to 1, what do I do to each of these values of u? We're adding 2 pi. What's maybe a more convenient way to add 2 pi? Adding 12 pi over 6. Pi over 6 plus 12 pi over 6 is 13 pi over 6, and then 11 pi over 6 plus 12 pi over 6 is 23 pi over 6. Haven't quite hit our metal detector yet. We're very, very close, obviously, so probably the next iteration of k will do it, but we should go ahead and check. When k is equal to 2, we're going to take our previous answers. We're just going to add another 2 pi to them. So 13 pi over 6 plus 12 pi over 6, that's 25 pi over 6, and we get 35 pi over 6, both of which hit our metal detector, both of which exceed what u is allowed to be, and so we throw them out and we stop. So 2 full rotations and some change is a little bit too much. We're done here. Do I have to worry about negative values of k? No, 0 is our lower bound. If k is negative, then we get negative angles. We don't need to worry about negative values of k. Theoretically, could we worry about negative values of k? Sure, there's no reason why k couldn't be negative. It's just, it's not going to give us solutions for this particular constraint, so we're not worried about it. All right, so I found 4 different possible solutions for u. Am I done? Am I solving for u? No, what am I solving for? Solving for x. And so each of these things, each of these values of u that I found is in fact equal to 2x. Dividing each one by 2, which is the same as multiplying the denominator by 2, the 4 x values that I get are, from when k equals 0, I get pi over 12 and 11 pi over 12. And from when k equals 1, I get 13 pi over 12 and 23 pi over 12. Yes, divided each one by 2, because these are all equal to 2x. Questions here with our first problem. The finding the bounds on k is not how I would recommend doing it. My recommended approach is just to check the values of k, because that's pretty easy. You just add 2 pi until it stops working, and then you're done. I think that's a little bit easier, but there was a little bit of interest in it from my 4th period, and I think from this class as well. And so I did want to show you at the very least that it could be done. We can figure out mathematically what k will need to be. And then we could use that information to then generate the solutions. And that's also a perfectly valid way to go about it. All right, let's take a look at B. Exact same idea. This is cosine of 1/2 x equal to negative root 2 over 2. Same constraints on, these are just going to be the standard constraints that I'm going to give you for x. It's pretty much just going to be this, that we're between 0 and 2 pi. All right, so same deal. What do I do here? So swap the 1/2 x to u. So u is equal to 1/2 x. And so we are looking at cosine of u being equal to negative root 2 over 2. And then what is my new bound on u? Where can u live? 0 to pi. Very good. All right. What are the nodes that I get? Three pi over 4 and 5 pi over 4. Of course, plus 2 pi k for each one. And so how could I maybe retrain pi here in terms of like the information that I'm actually going to be looking at? Just pi, just pi. 4 pi over 4. Awesome. So let's check some values of k. Yes. We have Bryce to check out, please. All right, he's on his way. Thank you. I'll have this uploaded this afternoon. Yeah. As well as yesterday's. Yeah. All right, so let's check some values of k here. When k is 0, what are the values that we get for u? 3 pi over 4 and 5 pi over 4. And what do we notice? We've already exceeded what u is allowed to be from just k equals 0. We can't have 5 pi over 4. Now, should we probably check k equals 1 just to confirm? It might be smart, but it's also pretty clear, I think, that adding an additional 2 pi to 3 pi over 4 is going to take us way, way, way beyond what we're allowed to be, that 4 pi over 4. So you could consider adding, like checking k equals 1 again, but pretty clearly we can go ahead and stop. There is only one value of u here, and that is 3 pi over 4. All right. And so we know 1/2 x is equal to u. So this is equal to 3 pi over 4. What is my solution for this equation? 3 pi over 2. So I wanted to show this one to highlight a couple of things. Up until now, we have looked at examples that have given us 2 solutions per full rotation around the circle. And that has been true when the coefficient in front of our x has been just a whole number. So that's often true. When it's like cosine of 2x or sine of 4x, you could imagine cosine of 7x, all of those would give us 2 solutions per kind of full cycle around the circle that we go. But when it's not a whole number, when we're looking at something like 1/2 here, or for example, we're going to skip this example, but example 4 in your packet, where you have pi over 3 as that coefficient, it is possible for you to get a certain number of solutions from one node and a different number of solutions from another. That's why we've been really checking these independently. We've been checking these values of k for both nodes because sometimes it works for one, sometimes a value of k works for one and it doesn't work for the other. And that's fine. It's just something that we need to be aware of. But beyond that, the process is exactly the same. And in fact, for something like 4, where we are looking at like sine of pi over 3 times x, you would do the exact same thing. Your bounds would get kind of messy. The upper bound on that would be like 2 pi squared over 3, which is a little bit gross, but not really problematic. You would just plug that into your calculator and check to see when the decimal approximations for your answer go beyond the decimal approximation for that. So it's not like more difficult, it just turns into a calculator problem rather than something that we can just kind of look at and figure out intuitively. Questions here with the bulwark? All right, then let's move right along then to example 5. This is sine of x times tangent of x is equal to sine of x, and we're given this constraint, which is that x is, of course, between 0 and 2 pi. Okay. Solving for x. So we've looked at a question that was somewhat similar to this. We looked at number 2, where we have kind of like x's on both sides of the equation. And with number 2, some people started off, they said, okay, I want to get all of my x's on one side of the equation. Let's start off by dividing everything by sine of x. And I said, okay, so it's not that like mathematically you can't do that, although that's a little asterisk that we're going to revisit here in a moment. The problem here is that you'll end up with like this plus square root of 3 over sine of x term when you divide everything here by sine of x. That's going to create some problems. It's not going to be very pretty. Much better is to resolve this without division, without introducing any sine of x's into the denominator, subtracting 3 sine of x from both sides of the equation, solving exactly like we did earlier. Here, we are not going to run into that same issue. All right? Dividing by sine of x doesn't create any kind of mess where we have like, some weird like root 3 over sine of x term, but it does potentially create issues. And this is just kind of a fundamental difference about like dividing a number versus dividing a function. What is potentially going to go awry if I try to start this off by dividing both sides by sine of x? What do I potentially run afoul of for certain values of x? Yeah, so there might be some values of x where I'm accidentally dividing both sides by 0. That's a problem, right? So we could approach this by dividing by sine of x, but it's only going to work for values of x where sine isn't 0. We would then need to manually go back in and check, well, hold on a second, what happens when sine of x is in fact 0? And that would kind of give us a full picture. That's one option. So one option is we could try dividing by sine of x, make a mental note, go back and check to make sure you didn't accidentally miss anything by dividing by 0. The other option that we have is to try and approach this without doing division at all. So if I wanted to collect all of my x terms on one side of the equation, how could I approach this without doing any kind of division so I know for a fact that I'm not dividing by 0? Yeah, we could like subtract sine of x to the other side. This would give us that sine of x times tangent of x minus sine of x is equal to 0. We've got something on my left equal to 0. It sure would be nice if the thing on my left was like a product, because then I could do the 0 product property and set both kind of pieces equal to 0. So what could I do to my left-hand side to turn it into a product? Factor out a sine of x. So now I have two numbers multiplied together. They equal 0. What do I know when I multiply two numbers together and get 0? What must be true? At least one of them has to be 0. And so from this, we get either that sine must be 0 or that tangent of x minus 1 must be 0. What are the values for x for which sine is 0? What are the nodes that we're going to get here? So pi is going to be 1. 2 pi is actually already outside the bound for x. So what's the other node going to be? It's similar to 2. It's coterminal with 2 pi. What about just 0? Right? That's coterminal with 2 pi and is included in like what my x is allowed to be. And we certainly could think about the plus 2 pi k here. There's not like we would want to theoretically continue using this. But what's the only value for k that's going to give me solutions here? Yeah, 0 is the only value for k. Any other value k, and you can check this, you can plug in 0, you can plug in 1, blah, blah, blah. But any other value of k is going to run afoul of the parameter that we have set, the constraint that we have set on x. And so while, yeah, it's probably smart to include them here, we actually don't end up really needing them here. Just simply because the only value of k that will work is 0. All right. So I got two solutions. I got x equals 0. I got x equals pi. And then tan of x minus 1 equals 0 tells me that tangent of x must equal 1. What are the nodes that I get from tangent of x being equal to 1? .45 degrees are in radians. Pi over 4 is one of them. And then what's the other quadrant where tangent is positive? 3. So this would be 5 pi over 4. And again, yeah, we could think of like the plus 2 pi k. There's nothing wrong with this. But again, the only value of k that's going to work is k equals 0. Again, you can check this, but take my word for it. Because of these constraints, because x can only be between 0 and 2 pi, k can only be 0. And so we get 4 different solutions, 2 coming from when sine is 0, and 2 coming from when tangent is 1. Now, we absolutely could have done the first suggestion that we ran through of like trying to divide by sine of x and then just kind of setting in our side that we'll need to manually check the zeros of sine to make sure that we're not breaking anything, to make sure that we're not missing any solutions. So for instance, dividing everything here by sine of x, I get that tangent of x equals 1, except when sine of x equals 0. So we are going to check this manually. And we're going to, we've already solved this. Tangent of x equals 1 gives us pi over 4 and 5 pi over 4 as solutions. I already determined that. So checking the zeros of sine manually, sine of x equals 0. That's going to give us 2 zeros to check, 0 and pi. And we're just going to plug those in, and we're going to see if, in fact, they are solutions to our equation. So when we plug in 0, we get sine of 0 times tangent of 0 is equal to sine of 0. And when we plug in pi, we get sine of pi times tangent of pi is equal to sine of pi. What are sine and tangent of 0? Yeah, they're both just 0 because tangent is sine over cosine, so 0 over 1 is going to be 0. And likewise, sine and tangent of pi are both just 0. And so both of these are in fact true statements. And so both 0 and pi also work as solutions. And so we get the exact same solution set that we saw from above. We just had to manually check to make sure that the zeros of sine were in fact solutions here. Yeah, Dylan. So we didn't have to check for the first way that we solved it, and that's because we never divided by sine of x. So we didn't have to worry about dividing by 0. We just organically found all of the possible solutions. The reason why for the bottom one we need to check is because the first step there is dividing out sine of x, which we can only do when sine of x isn't 0. So we have to manually check the zeros to make sure that we're not missing any solutions. In this case, we were missing solutions. I could have given you one where we weren't missing solutions, though. For instance, sine of x times cotangent of x equals sine of x would give you 0 times undefined equals 0, which is not something that we can parse. Because cotangent of 0 is undefined. So you would want to check whenever you divide by sine, whenever you divide by cosine, just make a mental, and you can get away with just never dividing by sine and never dividing by cosine. We did not have to do that. Like we could have approached this problem like we did at the top. But if you are going to, you need to keep in mind the possibility that you are missing zeros from the zeros of the function that you are dividing. Missing solutions from the zeros of the function that you're dividing, rather. Good question. Other questions with example 5 here? All right, let's take a look at 6, and then I'm going to give you guys some time to work through 7 and 8. So for 6, we are looking at sine squared of x is equal to, it's 2 sine of x plus 3. Is that right? All right. So you've got sine squared equals 2 times sine plus 3. What does this look really, really similar to? Almost a completely different type of equation here, minus the fact that everything here is in terms of sine of x. Something squared is equal to 2 times something plus 3. What is that an awful lot like? Well, I would make the claim that it's kind of like a quadratic. Other than the kind of complexity of the fact that everything is in terms of sine of x rather than just like x's, right? So we've got the variable, but in this case, it's the sine of the variable being squared, so on, so on. And so we're going to do what we did with our bell work. We're going to do what we did with that last example. We're going to take that layer of complexity, and we're just going to set it aside until the very end. We're going to use our u substitution technique here. Say that u is equal to sine of x. We're just going to set sine of x aside till the very end of the problem. And in doing so, we reformat this problem to be u squared is equal to 2 times u plus 3. Much more cleanly a quadratic. All right. So I now have a quadratic that I am trying to solve. How do I solve quadratics? What's the standard kind of methodology that we take? Yeah, we're going to factor. Before we can factor, though, what do we have to get on one side? Yeah, we need actually beyond just all the u's, we need everything on one side of the equation. We need 0 on the other. It always needs to be offset from 0. I don't like negatives in front of my squared term for quadratics. So I'm going to subtract 2u. I'm going to subtract 3. This is that u squared minus 2u minus 3 is equal to 0. What are two numbers that multiply to make -3 that add to make -2? Fantastic. U minus 3 times u plus 1 equals 0. And so the two values that I get for u are that u should be 3 and -1. Am I done? Did I find what I was looking for? No, I found u, but what am I looking for? X. So substituting back in that layer of complexity, this is really equal to sine of x. We'll start with the bottom one. When is sine of x, sine of what angle, is going to equal -1? Hmm? 3 pi over 2? Yeah. Okay. And then sine of what angle? What angle has a y value of 3 associated with it on our unit circle? Is there an angle that has a y value of 3 associated? No, 3 is way too big, right? Sine of x can only ever be between -1 and 1. And so this, in fact, does not give us any solutions. The only solution that we get is this 3 pi over 2. Questions with example 6? Yeah, Dylan. What is the theta that gives us a y value of -1? Yeah, zoom on. Yeah, technically it would be 3 pi over 2 plus 2 pi k, but are there any values of k other than 0? No, so I just kind of left it off. But you're correct. To be more precise, yes, technically the solution would be of the form 3 pi over 2 plus 2 pi k, but for the particular constraint that we're given, the only value of k that we care about is 0. Yeah. Certainly, I could give you, say, on like, I don't know, a test that you have on Thursday, an example where you would need to like do this process, and then there would also be that kind of k that you would need to check. Certainly, that is possible. So that is a good point to keep in mind. Yeah. Other questions here? All right. Let's take, we'll say like 10-ish minutes, maybe 15. Take a stab at 7 and 8. For both of these, both of them are actually very, very similar to 6. The issue that you are going to run into is when you attempt to do this U substitution, you're going to need everything to be in terms of like the same stuff. You don't want to have two different substitutions that you need to do. You also really don't want like two different kind of angles that you're working with. So think about how you could reformat the question that is given to, I don't know, either be like all in terms of sine or something of that kind of nature. So looking at the last two, very, very similar to number 6 that we did, but thinking how can we reformat what we have to all these if u plus 1 is equal to 0, that's -1, so what is the solution? Otherwise, it's speaking negative. Yeah, that was it. Yeah, sure. Yeah. And the whole like U substitution thing, you don't technically, like it's more aesthetic than anything. Like if you're comfortable like factoring things and getting like sine of x plus 3, sine of x minus 1 as like your factor, then you can go ahead and do that. I just set it aside so that it's more clearly working with it. Yeah. So you don't have to do that stuff. It's just one value. Yeah, exactly. Like yeah, it's like this is basically just as like if I just left everything assigned back and then work with that also be fine. I'm just doing it to make it easier. So how could we like reformat this to be in terms of like science? what is cosine squared? The same thing. Yeah. Yeah, that's okay. No, I'm great one. No, all I said was that if you solve it on like not the quiz itself, just direct me to whose paper that you used so that I could make that adjustment.
So that you already posted the last one.
No.
Oh, so I'm looking at
That's
it.
great.
Yeah. Okay.
Yeah. Yep. Like I said, technically it's squared, right? But like also it's just kind of one solution. Equals 2. Yeah. Yep. That's good. I like how you did that. No, yeah, I like that. That substitution. That's smart. I like that quite a bit, actually. Yep.
I won't be able to back.
No, you can. Yeah. Just replace all the sine squares with, or the signs with u. So you get like 1 minus u squared is equal to 2u plus 2, and then get 0 on one side. And yeah, definitely. So whenever you're doing this, I would work hard to get it in the order of like ax squared plus bx plus c. Because otherwise, like what you're doing becomes a little bit more complicated.
Yeah, I don't know why it's taking me so long to think of this, because this should be just 1 times.
You left off the plus 2.
Um,
Yeah, so this is 2u plus 2, that's what it's gonna be. Yeah, so when you subtract 1 from it, yeah, it'll become, yeah. You're correct, yours is not. Perfect, that's right. Yeah, and you can just ignore the substitution of that, like you don't want to. So we want to first switch this. This needs to be in terms of sign in order for us to replace it with u. So how could I rewrite cosine squared to be something in terms of sign? Thinking like what would our Pythagorean enemies allow us to rewrite as? Yeah, 1 minus sine squared. And then you could do the u substitution. So you probably get like 1 minus u squared instead, and then solve it. Yeah, that's good.
so like from here down to where your contract is.
Yeah. So that's the 0 product property. It says if I have 2 numbers being multiplied together, what must be true about one of those 2 numbers? One of them has to be 0. So you can set each of these equals to 0. Yeah, that's all you do. You set one equals to 0. Exactly. That's why it's important to be offset from 0, and it's why factoring is like a good way to go. Here u equals -1, and then when
Okay, that's
and then sin of x equals -1. What's the value of x?
No.
Like this. Yes, this looks good. You do not need to, because you are, when we do, it's only when we're substituting for like the inside of our function that we're gonna need to worry about adjusting the bounds. Because we don't even really like think about that with like the 2 pi k until after we've already undone the whole use of, so you don't need to readjust it. The answers are what you have here, where all the k's are 0, basically. Yeah, because you could check like k equals 1, but that's going to be 2. And there's nothing wrong with checking. It's good. You just, as soon as k equals 1, you're like, ah, well, number. So you can know easier. So, there's some temptation I think to like try doing what we were doing before with like substituting this. You're gonna run into an issue over here where we have like 2 different variables. That's gonna be an issue. So cosine of 2x. What do our double identities say about cosine of 2x? And there you have 3 options for those. There's one of those that will be particularly useful.
What else are we up on this test?
I can do it. I'll do it. Okay.
It's getting those. Doubles.
I would say you should probably be able to reproduce the sum and difference on it.
Okay.
So if I were to give you those, it would be mean incredibly nice. And then Pythagorean identities.
It's just these things.
Well, the double is just the sum formula, but where the alphas and betas are just like the same thing. And then the half is definitely what I would give you. I would definitely give you
The half I can't.
yeah, the half angle.
No.
Minus sine squared, so you subtracted. So here, I don't like having a negative in front of my leading term. I just think it makes things harder. So I would divide everything here by a -1, just like flip all of the signs from negatives to positives. Make sure remember that it's still all equal to 0, which is why we're allowed to do divide by -1. It doesn't like change anything. And then that should be more easy.
So am I gonna take this principle and go over to putting in?
Problem we're gonna run into is I would put like this one in terms of u and this one in terms of x, or even worse, like u over 2, and then that's just gonna be like this whole nasty mess. So how could I instead maybe like adjust this cosine of 2x or like cosine of 2 theta? So that so we have, so think double angle identities for that one. So how could I replace cosine of 2x with like our double angle identities in order to try it?
Double angle identities are,
It was like the sine of 2 theta, it was like 2 sine of theta, cosine of theta. Well, it was what we did in 5. All right, let's take a look at number 7 here. So this is cosine squared of x is equal to, what is this? 2 sine of x plus 2? My goodness. Please. All right, so what's the issue that we run into here pretty quickly? Why can't I just hop straight in, use substitute, create a quadratic, blah, 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 blah? Yeah, we're in terms of cosine on the left rather than in terms of sine. How can I refinagle this so that I'm only in terms of sine? Yeah, this is like 1 minus sine squared is equal to 2 sine of x plus 2. And now that everything is in terms of sine, we are able to switch out for u. I mentioned to a few people, this change that I'm doing is purely an aesthetic change. This is simply to make it very, very clear that I am working with a quadratic. So if this is not helpful to you, if you can just work with the 1 minus sine squared equals 2 sine of x plus 2 without needing to do this, you can treat it like a quadratic without doing the substitution. That's totally fine. You're more than welcome to. I'm just trying to compartmentalize the tricky part of this so that it's more clearly a quadratic. I don't like having a negative in front of my u squared, so the way I would probably go about this is adding u squared to both sides and then subtracting 1. Doing so gets me u squared minus, nope, not minus, plus, that's why I did this, plus 2u plus 1 equals 0. What are two numbers that multiply to make 1 and add to make 2? 1 in itself. U plus 1 times u plus 1 equals 0. And so what is my value for u? -1. Am I done? No, this is really sine of x. And what is the value of x? What is the angle that will give me a y value of -1? Three pi over 2. So exactly the same as what we did for the previous one, just one extra step there, reformatting that cosine squared into a 1 minus sine squared. Actually, same deal with 8, which is cosine of 2x. Yeah. All right. Same deal actually with number 8. The problem that we run into with number 8 is that it feels like this is almost like our Bell-work question, where we've got that cosine of 2x there. Problem is, if we try and substitute that 2x out for like a dummy variable, we run into this issue where our cosine is going to be in terms of one variable, our sine is going to be in terms of another variable, or worse, sine would be in terms of like u over 2, and that's going to be a whole mess that we have to deal with. Rather than dealing with that, let's try to use the double angle identities to see if we can't do something similar to what we did for 6 and 7. What is the double angle identity that is going to be most useful for me in this case? Cosine of 2x is equal to what? Yeah, it's probably the one that we should use. 1 minus 2 sine squared of x plus sine of x equals 0. With my u's, this is going to be -2 u plus u plus 1 equals 0. And then I'm going to divide everything by a -1 here, just because, again, I don't like dealing with this. So I get 2u minus u minus 1 equals 0. Two times -1 is -2. Two numbers that multiply to make -2, that add to make -1. Yep. -2 and 1, and I'm going to use my cheaty factoring magic here. That's going to give me u minus 1 times 2u plus 1. Equals u, and yeah, u is just sine of x. Yeah, probably should define that. Yeah. Good catch. My bad. Switching the colors was messing me up. So the two values of u that we get, I get that u should be equal to 1 and -1/2, but really these are both just sine. And so what are the value? Well, we'll start with the top. What is the value of x where sine of that value of x gives me 1? Yeah, so what theta will give me a y value of 1? Pi over 2. Don't forget well, in this case, we actually can forget it, but just to be precise here, plus 2 pi k. But what's the only value of k that we're going to be allowed to use here? Just going to be 0. So we don't need to worry about adding anything else. And then what are the nodes that I get for sine of x equals -1/2? I think 7 pi over 6 and 11 pi over 6. But again, what's the only value of k? Just 0. And so we end up with 3 solutions: pi over 2, 7 pi over 6, 11 pi over 6. Questions with 5, 5? Yeah, don't. No, we like for the bell work here, we did it in terms of cosine. That's fine. It's just a lot of these examples have been in terms of there's not like a rhyme or reason for it. Either is fair game. Either is fair game. Maybe we'll do a couple more cosine examples tomorrow just so that's more clear. Yeah, Oliver. Mm-hmm.
How do you go from side to?
So the double angle identity for cosine, the one that we predominantly used was cosine squared of x minus sine squared of x is equal to cosine of 2x, or cosine of 2 theta was what we were using back then. And then replacing that cosine squared with a 1 minus sine squared gives us this alternative form that's just in terms of sine. No, but it's if I have cosine of x plus x, this is the same as cosine x times cosine x minus sine x times sine x using our double angle or using our sum identities, which is cosine squared of x minus sine squared of x. So that's where the squared comes from. Is from the double angle. Yeah, it's a fair question. And then we replaced this with a 1 minus sine squared, which gives us the 1 minus 2 sine squared. Good question. Other questions here? All right. So we have about a little over, right about 10 minutes. If you guys would take this time to go to Schoology in the Unit 5 folder, as per usual, we have an exit ticket prior to our review. Let me know what you would like to see tomorrow for our review. Beyond that, there is also the 5355 classwork, and the study guide is currently posted to Schoology, for which I'll have a walkthrough posted at some point tomorrow. So got about 10 minutes left. Make sure you do the survey. And then beyond that, you're more than welcome to spend this time either working through the 5355 classwork, which is due tomorrow night, or working through starting the study guide. No, it's 20. I mean, it's the maximum value. It's effectively unlimited attempts. But the maximum I can give you through Schoology is 20.